Welcome to This Explainer. Today, we're breaking down a mind-bending geographic paradox that is going to completely shatter how most of us view the world. If you've ever, stared at one of those in-flight seatback screens and wondered why on earth your airplane is flying in this massive sweeping arc way up north just to get to a city that seems perfectly straight to the east or west, well, you are in exactly the right place. We're going to explore the fascinating geometry of our planet and discover exactly why straight lines are actually curves. Okay, let's dive into this. I want you to picture two cities located on the exact same latitude. Let's say they're both sitting right on the 45th parallel north. Now, if you're a pilot trying to save fuel, what is the absolute shortest flight path between them? For most of us, our brains immediately just draw a straight, horizontal line from point A to point B right across the map. I mean, it just makes intuitive sense, right? Keep it on the same line. But as we're about to see, relying on standard flat map navigation is a complete illusion. So here is our roadmap for today's explainer. Number 1, the 2D map illusion. 2, the spherical reality. 3, the math and the vertex. And finally, 4, real-world applications. All right, starting with section 1, the 2D map illusion, or the trap of the parallel. We've all grown up looking at flat rectangular maps where lines of latitude run straight east to west. On a 2D map, a straight parallel line looks, without a doubt, like the shortest distance. But on a 3D globe, unless you are standing exactly on the equator, a line of latitude is absolutely not the shortest path. Why? Well, because the Earth is roughly a sphere. The circumference of a parallel gets smaller and smaller as you move away from the equator and head towards the poles. Mathematically, the radius of a parallel is just the Earth's radius multiplied by the cosine of the latitude. So sticking to that parallel means you're actually tracing the edge of a smaller, way less efficient circle, rather than taking the true shortest path across the sphere. Moving right along to section 2, the spherical reality. Enter the Great Circle. And this brilliantly illustrates exactly what we're talking about. When you take the actual shortest distance between 2 points on a 3D globe and you force it onto a flat 2D map, it doesn't look like a straight line at all. It looks like a bizarre, wavy sine curve. Your eyes are practically screaming at you that this is a longer, wandering path. But in reality, out on the actual curved surface of the Earth, this continuous wave is a perfectly straight line. To put a formal name to it, this path is called a great circle. A great circle is defined as the shortest path connecting any 2 points on the surface of a sphere. Unlike those lines of latitude we just talked about, a great circle always shares the sphere's full maximum radius, and that makes its circumference equal to the entire circumference of the Earth. Think of it like this. If you were to slice the Earth exactly in half right through its center, the edge of that slice, that's a great circle. Now, what's really interesting about this is that because a great circle between 2 points on the same latitude doesn't just lazily follow that parallel, it introduces a really vital concept, the vertex. The path actually curves. In the northern hemisphere, it curves north. In the southern hemisphere, it curves south. The absolute highest point of latitude that this great circle reaches before coming back down to the destination is called the vertex, or the apex. So to take the shortest shortcut, you literally have to travel further north or south than both your starting and ending cities. Wild, right? Let's get into the mechanics in section 3, the math and the vertex, calculating the curve. So to find this exact route, navigational systems have to use spherical geometry. Imagine drawing lines from the very center of the Earth straight up to our two cities to create a plane. Calculating exactly where that plane intersects the Earth's surface gives us the precise latitude of that vertex. Systems also use a pretty cool equation called spherical linear interpolation, or SLER for short, to generate specific GPS waypoints along the curve at set distance intervals. This is what gives planes and ships the exact pinpoint coordinates they need to follow the curve perfectly. To see how this works in practice, let's look at a specific example from our source data. Step 1, we anchor our starting point at a specific city, like Seoul, South Korea, which sits at roughly 37 degrees north, 127 degrees east. Step 2, we choose a destination that is also exactly at 37 degrees north, but we increase the longitude difference, meaning we pick a destination further and further east or west. Step 3, as that longitudinal distance increases, the mathematics dictate that the great circle route bows further and further away from the parallel. Simply put, the greater the distance between the two cities, the higher the latitude of the vertex becomes. Let's move to section 4 and see how this all builds together in real-world applications, from math to navigation. All these complex SLR calculations are actually brought to life in interactive tools, like a WebGL-based Great Circle Vertex calculator. A user can input literally any shared latitude and longitude points, and the system instantly maps the Great Circle. It renders the exact GPS waypoints and visually proves just how much the route diverges from a flat line. This shifts all that dense data from a textbook right into the hands of real-world logistics planners. So the crucial point here really comes down to this number, 606. Let's take a real route on the 45th parallel, flying from a longitude in Austria over to a longitude in Mongolia. If an aircraft were to mistakenly just fly straight along that flat 45-degree latitude line, the distance is roughly 8,019 kilometers. But by calculating and flying the curved Great Circle route, the distance drops to only 7,413 kilometers. That is a massive savings of 606 kilometers on a single trip. And hey, it's not just those massive intercontinental flights either. Take a domestic U.S. flight crossing from east to west, again along the 45th parallel. Even on this much shorter route, flying the Great Circle saves 113 kilometers. But to get those savings, the aircraft has to curve up to 4 degrees of latitude higher. That means it actually flies about 440 kilometers further north into its vertex before coming back down to its destination. It looks like a huge detour on a standard map, but it's physically the tightest line you can possibly draw on the globe. When you start multiplying 606 kilometers or even 113 kilometers of saved distance by thousands of daily flights and massive ocean cargo ships, the real-world impact is absolutely staggering. This exact spherical math is what guarantees fuel efficiency, saves immense amounts of time and money, and drastically lowers emissions across global logistics. And beyond aviation and maritime shipping, these Great Circle waypoint calculations are fundamentally baked into GIS mapping software, geography education platforms, and even the autonomous programming for UAVs and drones. It's literally everywhere. So, we've moved from the illusion of the flat 2D map through the complex spherical math of the vertex and right into the real-world systems that guide global transport today. It completely shifts your perspective on how we navigate our planet, doesn't it? So I'll leave you with this. The next time you look at a standard map or sit back and watch your flight tracker curve wildly toward the Arctic on a long-haul flight, are you still going to believe a straight horizontal line is the shortest path? Thanks for joining us for this explainer, and keep questioning what you see.